All right, so let's look at more questions from the module 1, the phase behavior and stuff like that. Okay, so here we go. First question, we are given a phase diagram. I see that A to B line. Which of the following statements is true? The critical point for N2O occurs at approximate conditions of 180 M and 180 Kelvin. So 180 Kelvin, what we can do is we can mark those points actually. Okay, let me take a screenshot. So 150, and then I would say the 180 would be somewhere around here, nowhere near the critical point, and 180 M would be over here. So this is not the critical point. I think this is more closer to the triple point rather than the critical point. So that is incorrect. Option A is incorrect. Okay, now going back. A is out. B, at room temperature around 25 degrees Celsius. Remember, 25 degrees Celsius is 298 Kelvin because 273 plus 25 is 298 Kelvin. And N2O exists as a solid at pressure of 100 atm. So let's go to 298 Kelvin. So that's around 300. Okay, here's that line, 300 line, and then 100 atm pressure is over here. This is 100 atm pressure, and then under these conditions we are meeting over here now. Under these conditions, the substance N2O must be in the liquid phase because this is our solid, this is our gas, and this is our liquid. It's not in the solid phase, it is in the liquid phase. Therefore option B is out. Okay, get rid of those things one more time to keep things clean. Option C, the melting point of N2O decreases as pressure increases. The melting point. Okay, so when you say melting point, you're talking about the solid liquid boundary. The solid liquid boundary is this guy over here. Okay, because here we have solid, here we have the liquid. Okay, the point is if we decrease the pressure, melting point of N2O decreases as the pressure is increased. Okay, so if you increase the if you increase the pressure, let's say that you're going from this value to this value over here. Okay, so if that is the case, you can see that because of this curvature, the melting temperature increases when you increase the temperature, not decreases. So that is out as well. Okay, so friends, if we go to, just to make this clear here, let's say that you went from this pressure, okay, where we have a melting temperature of say 180 Kelvin, to this pressure over here, which is a higher pressure. Okay, at that point the melting temperature is going to be 250 Kelvin. Okay, so melting temperature increases when you increase the pressure, not decreases. So that is incorrect as well. So let's make sure that we make that note. Yeah, I could have just left it there. Anyway, so C is out. Option D, under normal conditions of 180 M. Yep, normal. Whenever I hear the term normal, I would love to draw this line at 180 M. 180 M and 25 degrees Celsius. 25 degrees Celsius again is 298 Kelvin. That is around 300. Okay, over here. Okay. N2O will be in the gas form. Yep, I like it. It should be in the gas phase. So option D is correct. So that's the only correct answer there. Option D. Moving on. Here we go. Question 2. You're given 3 wave pressure curves. And then if this submicroscopic representation corresponded to a mixture of the 3 substances, okay, you can see that this guy is in, okay, I can't draw here, let me take a picture. Okay. So what we have is we have two gases, no, give me a second. Yeah, no, one gas, and then two liquids. That's what we have here. Okay. Yeah, if this subatomic representation corresponded to a mixture of three substances at 20 bar of pressure. So 20 bar of pressure is this line over here. Bars of pressure and a certain temperature. What would that temperature likely be? Okay, now under these conditions, two of them are in the liquid phase. Okay, that means that point is above the curve for two of them, and for one of them it should be below the curve. Okay, so the most likely for this to happen, it needs to be in this region. Okay, so anywhere, any temperature in between -100 and I don't know -50, -30 would be a fair game. Okay, because under those conditions, let's say that we have a point over here. Let me have a different color now. Let's say that we are here. Okay, so this point is below the curve of methane, therefore methane should be in the gas phase, and then this point, the red X, is above CO2 curve, therefore that should be in the liquid phase, and also that is above the NH3 phase, therefore NH3 curve, therefore NH3 will be in the liquid phase as well. Therefore -200 is out and 0 degrees is out. 0 degrees is here, so that's out. 200 is over here, that's out. And then 100 degrees Celsius is over here. No, that, yeah, if we have the point over here, all three will be in the gas phase, so that is out as well. So the only correct answer must be option B, -50. Okay, we're gonna go with option B. Moving on, question 3. What is the normal boiling temperature for substance A? Again, whenever we say normal, all right, what I want to do is I want to draw the 180 m line over here. Okay, that's the line. We are dealing with 180 m pressure. That is what is normal for anybody on Earth. And then the boiling temperature means we are crossing the liquid gas boundary. These are vapor pressure curves. Vapor pressure curves, what we essentially have is liquid gas boundaries. And then since we're dealing with A, we are dealing with this red curve over here. Okay, and then the liquid gas boundary interacts with this or touches this 180 m line at this point, and that must be the boiling point for this substance over here. So it should be between -5 and 0. It should, and the closest one is -4 degrees Celsius. So we're gonna go with that. Okay. Moving on. Question 4. Identify the phase change occurring in the transition from condition A to condition B based on the transitions occurring in the phase diagram. Oh, wait a second. It's a huge question. Yeah. So you're given condition A and condition B. So what we're noticing here is we are going from a gas to a solid because you have more organization. So the question is, which transition are we referring to? Wow. All right, I think this is good. I'm gonna go with this. Let's take a screenshot. And here's my page. I'm gonna switch to blue. Now, this weird A with an accent is indicating an arrow, okay, going like this, by the way. Sometimes this happens with Mac OS, Mac operating system. Anyway, I just want to point that out. Okay, now we're going from, according to this condition, I would say this is a gas and this is a solid. I mean, notice that I did not consider this as a liquid. In a liquid, yes, particles are closer to each other compared to a gas, but still there's some more randomness. Particles can move around freely, okay? But you can see that in this case, these particles or molecules are kind of organized. and then that is characteristic of a solid. That's why I'm saying that we are going from gas to a solid, not the other way around. Anyway, that means we are crossing this boundary over here, the solid gas boundary. This side we have solid, this side we have gas. Okay, now that means going from 2 to 1, gas to solid. We are going from gas to solid. Therefore, we are crossing this boundary in this direction. Question 5. Let's take a screenshot one more time. Okay, what are the phases of A, B, and C at 180 m and 40 degrees Celsius? Again, when we say 180 m or normal conditions, I would say that, I would always draw this line out, okay? And 40 degrees Celsius is over here, okay? So we are at this point, this red point over here. Now the question is, under these conditions, 180 m and 40 degrees Celsius, what would be the phases of A, B, and C? Okay, now remember again, these are wave pressure curves. Okay, when it comes to wave pressure curves, what we have is the liquid gas boundary. Okay, because this is pressure, this is temperature, and then this is coming from a phase diagram, solid, liquid, gas, and is this part which is represented over here. Okay, now anyway, just a reminder again, above this line we're gonna have the liquid phase, and below this line we're gonna have the gas phase. Just like here, we have the liquid phase above the line and the gas phase below the line. That's the idea. Now this red dot over here is above the line of C, meaning C should be in the liquid phase. Okay, so if this was C and then you are over here, then it should be in the liquid phase. C should be in the liquid phase. Okay, so anything that says C is a gas is out. It's a gas is out. Gas is out. So we only have 3 options left. Okay, and then again, this dot or this red dot over here is below the lines of both A and B. Therefore, both A and B should be in the same phase. And then that must be the gas phase, because if you are, let's say this is A, okay? If you are over here, that means you are below the line, below the wave pressure curve. If you're below the wave pressure curve, you are a gas. So both A and B are in the gas phase. And then I am staring at this particular answer over here, which looks very nice. And then this is out. All of them are not in the same phase. And then this is out as well. B is not in the liquid phase. B is also in the gas phase. So the correct answer is the second option over here, and we'll select that. A is gas, B is gas, C is liquid. There you go. All right, moving on. It's the same. Here's not another one. We have seen this before, the wave pressure curves. The question is, what is the most likely phase of NS3 at 0 degrees Celsius and 1080 m? Again, just make sure that you mark these conditions in the phase diagram or the wave pressure curve diagram. Okay, so we have the 10 bars. Let me see if I can do it. So 10 bars between 0 and 20, the middle way. Okay, here's my line for 10 bar. And then and 0 degrees Celsius is over here. Okay, so we are at this point. Let's call it an X. Okay, now the question is, what is the most likely phase of NS3 at 0 degrees Celsius and 10 bars pressure? So again, here's the wave pressure curve for NS3. Okay, and then clearly you're above the line, so you are over here. Okay, above is liquid and below is gas. Because you're above the line, the NS3 must be in the liquid phase. That's it. So that should be option B. Okay, So going back to the quiz, we'll select option B, liquid phase. Moving on to question 7. Let's take another screenshot. Here we go. Okay, which of the following graphs best represents the change in total energy, delta E, versus temperature as N2O goes from point A to point B? Starting here, we're ending up here. Okay, now that's cool. First of all, the first thing we need to realize is we are cooling. We are going from a higher temperature to a lower temperature. That means we are cooling. Okay, if we are cooling, then heat is released from the system. Therefore, delta E must be less than 0, or delta E must be negative. Okay, therefore, I'm going to eliminate options A and D right away without thinking too much. Okay, and then again, if you look at option B, we can see that we have this horizontal region over here. Okay, this tells me that temperature increases. Actually, okay, let's say temperature decreases or increases, or temperature changes, but the energy does not change. This cannot happen. If the temperature increases or decreases, if the temperature changes, then the energy has to change. Energy has to increase or decrease. Remember, temperature is a measure of the average kinetic energy. If the temperature increases, the average kinetic energy increases. If the temperature decreases, the average kinetic energy decreases. So therefore, option B must be out for that reason. And that leaves us with option C. Therefore, that should be the correct answer. But just read, let's try to read that. Let's try to make sense of this as well by considering what we know. Oh, and again, when we talk about, or when we read delta E versus temperature graph, okay, we always start when delta E is equal to 0, because at that point, delta E is equal to 0 means energy hasn't changed at all. Okay, and energy hasn't changed at all only at the beginning, because we haven't touched the system yet. Okay, so we always start at this point over here. So we are starting at a higher temperature. Okay, and then when you decrease the temperature, energy decreases. Okay, so we are going from, this is our gas. Okay, so when you decrease the temperature, we are decreasing the energy. And then during the phase transition temperature, okay, the temperature remains constant, but we keep removing energy from the system. Okay, and that's why energy decreases. And then this should be the gas to liquid phase transition. And then once everything is converted to liquid again, energy decreases with temperature, the liquid phase over here. So that's how we can make sense of the correct answer here, which is option C. All right, option C is selected. Okay, I think this is the last question. Question 8. All right, let's take another screenshot. Okay, now what is happening here is a pressurized fuel tank carrying liquid methane at minus 160 and 10 atm pressure started leaking into the outer space when the temperature is very, very low, minus 270 degrees Celsius. It's closer to absolute 0. Okay, based on temperature, it should freeze without a doubt. And at the same time, the pressure is decreasing as well, but we don't want to complicate things. But let's say we know for sure the pressure, the temperature is decreasing. Okay, so again, when we read time, we always start from the left and goes to the right. Time increases. Okay, therefore, anything that says the temperature increases with time, just like option B over here, is out. Because option B, we're starting at a lower temperature and ending up at a higher temperature. No, that is not what is happening. We are starting at minus 162 and ending up at minus 270.3 Celsius. It should be decreasing. And also, this is out as well for the same reason, because again, we're starting at a lower temperature and then we're ending up at a higher temperature over here. That is not possible when it is cooling. Okay, things are getting cooled down here. Okay, and then we are left with options A and D. In both cases, temperature decreases with time. Now the question is, when it comes to option A indicates that there won't be a phase transition. That means right now we have the methane in the liquid phase. When it cools down, it's going to remain in the liquid phase. Okay. But we know that, I mean, we are starting somewhere around, let's see, I mean, somewhere around here, and then ending up something closer to somewhere around here, right? Okay, very cold, and then very low temperature. You can see that we know that this is solid, this is liquid, this is gas. So I would think that, I would assume that the methane is going to become solid here. Liquid methane will become solid. Okay, considering that there's some pressure, it's about 0 atm. Let's say that there's some pressure, and at least around the spaceship, therefore there will be some pressure, and then that will cause methane to undergo a phase transition. Okay, and during phase transitions, temperature does not change. Temperature remains constant. Out of A and B, there's only in D that shows as the temperature remains constant, indicating a phase transition. For that reason, option A is sound. Our correct answer would be option D. Again, the point is, we are cooling. The temperature goes down with time. Number two, that's a phase transition. And during the phase transitions, the temperature remains constant. Okay, so we need to have this region over here. Where time goes on, but the temperature remains constant until the phase transition is complete. Okay, so that's